breakfast ready?
Breakfast is ready, indeed. Good morning, welcome back. Schekman, Michael Boer, just the two of us today. Toasting design number 11. And today we're going to be talking about iteration, optimization, and maybe one other thing as we fit it all into design and how we're going to do that.
So what does optimization mean to you? Because students seem to think, oh, I'm going to optimize this design. That's the classic thing that's said.
Sure.
So what does the word optimize mean to you?
Taking it to the best possible state.
Yeah, and how do you define best? I mean, what is the best ice cream flavor to you? Is it the best for me?
No, well, exactly. It's the sort of best compromise.
Okay.
Because you can't satisfy every requirement. You can't just go and say you can't just pick one of your criteria or one of your particular requirements and say, I'm going to optimize the hell out of that. It can accelerate at 500 meters per second squared, but it can't turn, it can't take off actually, it can't actually ever stop or anything like that. It's effectively optimized in a degree, but that's not proper optimization.
Okay, I would agree with that. So optimization is trying to get the thing that is being designed, the complex system, the simple thing, the part, or whatever it is, to perform as well as possible.
Yeah.
So then what does the word iteration mean to you?
Iteration is...
I'd say it's working a change through the design.
Yes.
And then optimization is the interpretation of the net outcome.
Yeah,
so
actually,
that
that's
little
brilliant.
change all the way through. So the example which I came up with, which we could sort of just run through. I mean, with aeroplanes, every single flippant lecture in third year covers the difference between these things, and
Sure.
and I call it the sort of and then story. Okay, you want to make this thing a little bigger, okay, and then and then.
Yeah.
Right. So we have a race car.
Sure. Cool.
Right, it has been designed, a bunch of students, but it's for a upcoming long endurance race.
Right.
Okay, so there are multiple systems in a race car. There's the grip system, the propulsion system, the safety system, all of those lovely, funny things.
Sure.
Even the marketing system.
Yeah.
For our industrial friends. Right, so long endurance. If you wanted to optimize for long endurance, what does that even mean?
Okay. Basically, straight off the bat, I mean, long endurance, you need a fuel tank. You need a decent sized amount of fuel so that it can have a decent endurance, depending on race rules and refueling and so on and so forth. It means it needs to be able to stand up to loads for a long time.
Without
cracking things. So, I mean, taking into account repairs and things, you don't want to have to keep welding your chassis back together every 100 meters.
Especially if the crack is under the fuel tank.
Sure. No, I mean, that's a great place to be welding there.
All right, so if we try not to complicate things too much, if we run through the sort of make one change, and then the process of iteration is to sort of come up with all the mathematical equations which are involved in forces, and then those forces go here, and then they get maybe diverted and converted into moments or stresses or whatever the case is.
Yeah.
Right. What's the most important starting component that we could say experiment with long endurance cars? And I'd say probably tires. If we started with tires.
Cars pretty much come down to the tire.
Okay, cool. So we've got this car. We now got several sets of tires. Each of those sets of tires might have different contact areas, might have different rotating inertias.
Yeah.
Okay, cool. So now we put one on which is a much higher inertia tire, but it offers lower rolling friction, and it offers better grip because it's a very kind of corner heavy course
track. Yeah.
That higher spinning inertia with better grip is going to need, say, a slightly different set of brake disc, brake pad combination. That different spinning inertia is going to, number one, also add mass to the car, and it's going to mean we need different spring constants and different spring dampers
Your
for the
suspension system is going to be majorly affected.
Because the suspension behaves differently, the loads on the chassis will change.
Exactly.
Which means we might end up with a torsional problem.
Yeah.
If the torsion is too much, we need to stiffen it up.
Yeah.
As we stiffen it up, we can only do that by either redesigning the whole thing or else by adding structure.
Extra members, yeah.
Adding those extra members adds yet more mass. that mass is in a, let's call it, bad location from a weight distribution front back.
And not only that, is now you're increasing the load going into your tire, which means your tire might not be even good enough anymore.
Correct. But it's that mass problem that now you're left with, well, there are two, and this is where you just jump into concepts and you can use TRIZ. Well, that mass is right near the front. We need to get the mass to the back. Well, we can solve a mass problem by adding more mass at the back, but that makes the whole thing heavier.
Or split the mass up or whatever.
That's right. Or we could fake the mass with a downforce term, but then we don't have equal mass distribution across the speed range, which might be good, might be bad.
Exactly.
Once we've sorted all that out, if you solve it with a downforce problem, that's a drag issue. So now you've got more mass, you might have more drag, which means acceleration comes down, but deceleration might go up.
Exactly. Yeah.
All right. Well, that might be good, it might be bad.
Yeah.
If we solve it with a mass redistribution by, I don't know, moving the driver's seat slightly forward and moving the firewall and a bunch of little minor redesign things, we could end up with a car which is perfect to put on a racetrack with a race driver to get a lap time.
Yeah.
And only then have we iterated the design.
Yes.
To get data.
And in iterating it, and sort of reading out, okay, this is the result of these iterations, we are then looking at optimizing it from there out. So it's if I've understood that correctly, it's right, we got these answers, now this mass, now this acceleration, now this deceleration, etc. And is that then good enough?
Yeah. And I mean, we use the example of trying to chase just one little factor, a change in tires all the way through.
Yeah.
But I guess if we were smarter about this, we could cut where the suspension joins the chassis. And if we had a model of that, we could pre-model different wheel combinations with that system in isolation.
Yeah.
And make the changes there so that let's call it the loads and load parts on the chassis were sort of unchanged regardless of tire.
Sure.
That would be the smart way to do it. But that would be an iteration and actually trying to optimize the suspension so that you could have wet tires, dry tires, and the loads are basically the same. Okay,
so for you, how would you, when you've got this route for iteration, we identified mass in this particular situation. Yes. Mass is the key one. How do you go about identifying that is the thing that we need to iterate through, or that is the sort of guiding factor that we use?
Oh, so how do you know what to start with?
Yeah.
I always try and work backwards.
Okay.
So, I mean, in the aircraft design sense, I need a bit of extra range. Okay, what are the main things that go into range?
Sure.
Well, there are four forces, and there's primarily the pitching moment.
Yeah.
If you cut one of those down, it's either going to give you a mass save or a area save, which is a drag save. But if the area comes down, there's center of gravity issue, but there's also then a drag save.
Exactly.
And I try and work backwards as to what ingredient has the biggest effects on the pie.
And in so doing, you're also getting you're not staying, it's not, let's look at the engine and then designing this engine for this aircraft so close into it that we're only iterating within that small bubble of the engine. We've got a larger scale idea as to what's happening for the entire system, the entire design.
And I think a very valuable point there is if you talk about sort of high performance equipment, racing cars, airplanes, wind turbines, things like that, you can iterate and optimize in isolation.
Yes.
I mean, if you take the good old electric drill, the overall size and shape has remained the same. But if you were to take the covers off, motors have changed dramatically, but they've left everything else the same.
Yeah.
And I guess we could call it micro or macro iteration, and then micro and macro optimization.
Yeah. Well, I mean, that's iteration. I mean, because we're looking at it, iteration in two sides here. We're looking at it in the sense of while I'm designing, while I'm going from a nothing to a solution to my problem that I've identified, I'm iterating within that.
Yes.
Now I've produced the product. It's out there. It's selling. People are buying it, or your boss wants it, and we're using it within the company, whatever the case is. Now, with that product, that solution, let's iterate solutions.
Yes.
I mean, so the example I can think of quite easy if we say look at Spitfires in World War II. From the Mark 1 to the Mark 24, the iteration and thing is, and it's based on different factors.
Yes.
It's not based on, all right, let's necessarily get, the thing to actually work per se. It's let's have a better fit in this new situation it's in, or with this newer engine, Griffin from Merlin, or whatever the case is. we need bigger cannons, or different cannons.
Engine's heavy, need longer nose.
Exactly.
Propeller gives more torque, need a bigger rudder.
Right, we don't have a good enough roll rate anymore, so let's clip the wings.
Yeah.
Visibility is poor, let's put a bubble canopy on.
Yeah.
That's a different level iteration. So in terms of that, what do you think is the basis that kind of kicks off? We can look at it and start saying, okay, within our design, our mass is too high, or whatever the case is. But let's say now you've got your product, it's sitting out there on the runway. What do you think? Let's say going from Mark 1 to Mark 5. I know there was the 2 in between that. But what would you say for the Spitfire was the sort of guiding point that said, okay, we need to shift from the Mark 1 to the Mark 5?
The Germans.
Fair enough.
The sort of liftoff had quite a strong influence there.
Okay, but so the Germans sort of instigated, say, okay, the vehicle's not good enough.
Yes.
But what I'm saying is, okay, we know it's not good enough. We have a system. Yeah, it's maneuverable. Yeah, it's sleek. All that good stuff. And they then made changes to get to the Mark 5. What do you think instigated those particular, or not instigated? Why those changes?
I think it's relatively simple in that, number one, the British really only had 2 fighters.
Sure.
They basically ordered the Mustang from the Americans as a kind of backup.
Yeah.
The first ones were quite rubbish, and the good ones were only ready in the end of 1944 anyway. But the Spitfire had a higher performance than the Hurricane.
Yeah.
So it was easier to achieve if you iterated the design.
Okay.
As opposed to up. And the Hurricane was limited based on aerodynamics and the structure used to build it. So the Spitfire was a more bang for your buck, if you say. And the other thing is, if you end up with an increase in power, so 1,000 horsepower to 1,450, and you then get, say, 40 miles an hour extra speed, you can then say, all right, Rolls-Royce, can you keep going?
Yeah.
Because if you can do that and you can get on, then we can do the sort of next version. I think what is important to note is that basically the Spitfire wing, in terms of area, didn't really change until the very sort of last marks.
Yeah.
But there's that classic thing that the very last Mark Spitfire was equal to the takeoff weight of a Spitfire Mark 1 plus 32 passengers and baggage for the same wing.
Sure.
And it was 120 miles an hour faster, and the firing rate, I think it fired 25 pounds of lead per second versus 4 pounds of lead from the Mark 1. And same wing. And the problem with the Messerschmitt 109 is it was originally designed with the wing about 2 square meters too small. So even though they kept adding power, its wing loading ended up being behind that of the Spitfire.
All right. In that case then, I was looking at, we've got our 2 main words we're looking at now, iteration versus optimization. If we go for that sort of improvement through models, look at it through cars, you got a Ford Fiesta, the old Ford Fiesta versus a new Ford Fiesta. Is that iteration, or is it optimization, or is that just getting locked up in word definitions?
That's an interesting one, because actually how much is different? Okay, it comes up with different mags, it's got a new dashboard, but if you open up the engine bay, how much of that stuff is actually brand new design from scratch?
Sure. If we looked at it at a high-level design, if you were to produce that high-level design, you'd basically be able to match the Ford Fiesta at the same times in both of them.
Yes.
Okay, I mean, maybe we don't know enough about cars to be commenting.
I would call that iteration. It's an iteration of the design. What has actually improved? And the thing is, if there's a dramatic improvement,
sure,
you've iterated the design and it's a whole lot better.
Okay.
But fuel consumption over the last 10 years hasn't really changed in cars. It hasn't got dramatically better. I'd say from 20 years ago to now,
sure,
there's been a huge improvement.
Yeah.
But, currently, if you compare, let's use the Fiesta as an example, as opposed to the Fiesta to one of the sort of micro cars that are coming up, that would be optimization of the inner city car, because it's it's specifically designed for short duration, super low fuel efficiency.
Okay. So in terms of then when we looked at a lot in terms of the iteration for a design. Now we're going back to within our design. We've gone from how we would in our projects for undergrad courses. When the students are told you now need to optimize. What do you think are the sort of criteria points, not PRS criteria, but the standard criteria points that should maybe be considered or looked at, or?
Well, I would say that undergrads don't really need to optimize. It's certainly a complex system. I would say the students need to sort of come up with a Mark 1 model.
Okay.
And then they need to say, all right, this is the Mark 1. I've done almost all of it in the case of the Spitfire.
Yeah.
And, well, there's this new engine. And I've iterated the design through to tell you how much better it will be. And then against my criteria, this is the right thing to do.
Okay.
As opposed to sort of, if you know, going back to the racing car example, if we kind of find this new nanotech to reduce the car drag, how do we optimize the placement of this stuff on the outside?
Yeah.
What a student should be doing, particularly at third year and even fourth year, is identify something and then just work it through so that you've actually got a numerical target to say it is better by about this much. And I think that's probably okay. If, however, you are trying to design the perfect stub axle for this racing car, the word optimization is completely different.
How so?
In that you're going to be running a design of experiments model and a detailed finite element model, because you're going to be optimizing the thing for, you know, long life, lightweight, low mass, with 15 different materials, with 25 different heat treatments, etc. That's where optimization comes out, that you've got a well-designed shaft. So the working stresses are good, but how do you make this thing outperform, say, a competitor?
Sure.
And that's where optimization comes into it. So I think it's more down to at an undergrad level, optimization is more when you're down to components.
Yes. No, I like that. At the same time, though, fundamentally, I'm always very hesitant with students getting too locked into definitions and, this is definitely this and this is definitely that. When you're designing something, you can't just, all right, I've got this number, therefore it's 5 millimeters. This bracket's 5 millimeters. This weighs 2 kilograms. This weighs this. What I want to see is your awareness of what does that mean for the design?
Yes.
So now that it weighs this amount, what is the significance? What role does this play on every other system? What role does this play, or is this good enough? Can we make it better? Are you understanding of that? And involved in that is various processes in various levels of optimization iteration. If you cannot show me that this is the best system, or that you understand it's the best, or how it could be the best, or whatever the case is, even if you haven't managed to get it to that best point, but you know what next step needs to take place and what effect that may have, you're not just guessing your way in the dark to actually get a final solution, then that's what I want to see. That to me is, in terms of an undergrad level, a design. You'll go through various steps of iteration. You'll go through various steps of optimization as the need arises and as necessary. But don't try and race to that point of saying, all right, I need to do X amount of iteration, I need to do Y amount of optimization, and I'm therefore done, regardless of whatever your system is. Because your design is judged based on the solution.
And how much, do you come up with your Mark 1 design and put that in the report and then say, oh, well, it works, but now I'm going to have a go at making it even better. You then make it better.
Yeah.
You still have time left in the project.
Sure.
So then you try and make it better still. If you put all those steps in, is that a good report? Because what I'd rather have students do is identify the Mark 1 and then say, these are the areas, and then explain what the iteration was of the optimization. And then, well, it results in this and then work on understanding why the improvements happened, as opposed to, I've got a mathematical model between wing aspect ratio on this racing car and wing thickness to chord and angle of attack and top line speed. Okay, well, wonderful.
Yeah.
But what about your acceleration profile?
Yeah.
What about your fuel consumption? And is the overall thing better? So is it any better?
Yeah, it's trying to do too much, and in doing so, trying to go through too far into the design, trying to make it too final, I guess you could say. And in doing so, you're never able to really give enough of the steps in between. You're skipping them. Yeah. And that's sort of something that then ends up because you're not giving enough, you're judged based on what you're communicating, or what you're telling us. So as good as that final design is, because you're not actually, and it's likely because you're also not thinking of it enough, you're trying to move it too fast, so you're doing too much of it too short a time. Your final system is just too small, it's just too weak and too fragile in terms of everything that holds it together.
And I think as a a caveat to that is what we're really not saying is don't come up with rubbish as your first design and then try and optimize it.
Yeah.
That's bad.
Yeah.
Rather, spend your time and come up with a very good first attempt, which works properly.
Yeah.
And if time is up, that's fine.
Yeah.
And that's what is expected as the kind of minimum level of what's required to pass design. That's going to get you a good 60, 65, 70%. You've got a design that works. A student that is an A student for design, which has got nothing to do with the other technical courses, is your first attempt is really good, and you've understood exactly how to improve it for a variety of different side targets.
Yeah.
You design a perfect aeroplane. The third year seem to love firefighting. So you design a perfect passenger aircraft, but then you say, well, if you do this and do this, the drag goes up by 2%, but you can go and you basically extinguish Australia with it. You then have demonstrated that you've got quite good design skills.
Yeah, and you know your design. I mean, that's fundamentally what I want to know, is that do you actually understand the system you've created? Do you know what it can do? That it's not pure chance that this thing happened to sort of materialize in front of you, that you created it, you developed it, and it works and whatever, and you understand how it works, whether it works or whether it doesn't. I think it's enough for this one. Cool, thanks very much. Catch you guys up later.